So several people say they're interested in giving presentations today, which is fine. As recommended by Nick, I'm going to say use the classroom built-in computer for these. So put your slides on a USB stick or something and put them in there, unless you're happy logging in on the classroom computer to get it from your cloud account or something. Hopefully we'll get good resolution and all that, so we won't have the slides all cut off like Liz's were. He said, that's what you should do for these presentations, and I think that's reasonable. I got a USB stick if you need one. We'll have a normal lecture, and then we'll have a break, let people set up, and then people can give talks. You get extra points if you give your talk this week. The time I planned for it was next week, and that's why I made no task due next week, so people have time to prepare their presentation. People that did not get credit for task 3, of which I know there are quite a few, they might consider doing a task that week anyway to make up for it or something. Anyway, any questions about anything? I know we got at least one person that's not in a group. If anybody's not in a group, at the break or after that, talk around, find people, join a group.
So quick question, are we actually supposed to present a visual as well?
Not necessarily.
Okay.
Just 5 minutes to present something about security. You can do it without slides, which is perfectly fine. Some people, by visiting speakers, some of them don't use slides. Just depends on your topic.
Okay.
Good. Doesn't have to have visuals. Doesn't have. Another thing you might do is a live demo of something, although usually in 5 minutes it's not enough. Yeah. You do not need to use slides unless you think they are required to make your point. In 5 minutes, you've really only got enough time to make one point. And you don't really need slides for that. In fact, in management type positions, managers often don't want to see pictures. They just want to hear the point. It's perfectly fine. All right. So, this is security engineering. This is pretty much the summary of A+. So there's a lot of facts in here, but I hope you already know most of it. Although a little bit of it is new. The security models is special stuff I never saw anywhere except the Security Plus, and this, or except CISSP. And this is actually pretty interesting. This is when I first learned about my CISSP, this I thought was the most interesting new stuff, is the mathematical sort of intellectual models behind security. I thought that's interesting. So here's the security models. There's quite a few of them, but the main ones are Bell, LaPadula, Biba, and Clark-Wilson. The rest are minor variations on them. And the way to remember, those three came up in order. Bell first, then Biba, then Clark. And they came up in a very logical order of what you think security is. So we'll talk about them. And here's the basic idea. Think about a military model. All these models were designed thinking of the military model, where you have unclassified stuff, confidential stuff, secret, and top secret. So you call that going up, and you call this going down. And now the issue is whether you can read up would mean a person with a secret clearance could read something at top secret, and if you can read down, a person with top secret clearance could read something at secret. And then there's write up and write down, and that's what all the models are about, which combination of those operations should be permitted. So the simple security property, as you would think, the first thing anybody thinks about security is secrecy. How do you protect the secrets from people that can't be trusted with the secrets? So the first thing they want is confidentiality. This is a long time ago, back in the 70s. This is the thinking that eventually led to the modern thinking of confidentiality, integrity, and availability. But the first thing people thought is you just have to keep the secrets. So this is the simple security property, no read up. Obviously, you don't want people that are only cleared for secret to be able to read the top secret stuff. You don't want people that are uncleared for anything to read in a confidential secret or top secret. That's what you mean by a secret. You cannot read anything above your level. That would seem like an obviously good thing to do. This is what the Bell-LaPadula model does. I think there should be an L there. That's the plan. This protects confidentiality. No read up. Writing up is okay. You could take information from a low security level and write it to a higher security level, and that would not do any harm. That's fine. You may discover something at a secret clearance that's then classified top secret and moves up, and that doesn't hurt anything. But you can't write down. If you were to take top secret stuff and then write it down to secret, that would reveal it to the people that aren't cleared for top secret, and that would screw it up. So it's no read up and no write down. That's the simple security model. That would seem like all you have to do. And it turns out that this actually doesn't work as well as you think, and that's why other models were needed. But this is what the first logical model was of security. So read down would be if people at a high level can read things at a lower level, and that is permitted, of course. That doesn't violate confidentiality. If you're cleared for top secret, you can read secret or unclassified stuff. That's fine. Now, these things are called state machines. That's how computer models these things are. You have a network of computers and transistors and files and people and printers, and they're in a certain state, and they can move to a certain other state, and you allow certain motions and you allow other motions, like you don't allow a write down. So there's a state with the top secret file on the top secret server, and there's a state with the top secret file on the secret server, and you do not allow that to happen. That's why it's a state machine, and certain motions are allowed and other motions aren't allowed, just like a little game. So if you can prove that if you start in a secure state, the only allowed moves maintain your secure state, then you understand you got a model that protects the data correctly. That's the mathematical sort of underpinning of this. So the Bell-LaPadula model was for the Department of Defense. It maintains confidentiality, and that is all it has. 2 rules: no read up, no write down. That's what they call it. Simple security policy and the STAR security policy. All right. This maintains confidentiality. The problem is it does not maintain integrity. People with low security clearance are allowed to write up so they can alter data at high security levels even though they can't read it. And that means they can perform sort of denial of service attacks. That is a problem. You don't have integrity in this model. All you get is confidentiality, and this is how they began the thinking that would eventually lead to realizing there are 3 things: confidentiality, integrity, and availability. They can't all be perfect. The first thought was to protect confidentiality, and the consequence is you lose integrity. There's a tranquility property, which says security labels don't change while it's operating. There's a weak tranquility property, which says labels can change, but they don't change in a way that breaks security. Anyway, there are lattice-based access controls wherever you have various kinds of classifications like clearance, need to know, and role. So there's more than just one dimension, not just up and down, but there's need to know sideways and role, which might be another way. And then you'd have various levels here. That's the lattice-based model, where you'd have these things like alpha, beta, gamma to reference your available motions in 3 dimensions through this complicated world of security. It looks something like this. The highest person can do alpha, beta, gamma. Other people can only do some of them. And these reflect different combinations of need to know and clearance and role in the structure. So that was the first one. The BIBA model was the one to replace it. And this is exactly the opposite. This is a model that creates integrity. No write up. So a person with low level is not authorized to change anything at a higher level to maintain the integrity. And the other one is no read down. The people at the high level are not allowed to read things at lower levels because they might put that data back up, and that would corrupt things. This reminds me of the Catholic Church, where you have this one thing at the top of the Bible, and everybody's allowed to read it, but nobody's allowed to change it. So you maintain integrity. The document at the top cannot be modified, but of course you have no secrecy. Everybody can see it. And this is where you begin to see the fundamental contrast here. There was a story I read, one of these security books. The KGB broke into a safe in Washington and stole a secret document, and when they brought it back to Russia, they found that another team from the KGB had already stolen the same document. But since they never talk to each other for all the secrecy, they don't know what the other teams are doing, and that's what happens with secrecy. Since nobody can find out anything, people undo each other's work, and they don't work together, and that's why, now the FBI is saying somebody gave them a tip about this guy that's going to shoot up the school, but people don't talk to each other, they didn't work it out. It's an issue. So secrecy has unexpected costs, and one of the costs is integrity. So the BIBA model creates integrity, but it does not protect confidentiality. And this turned out to not just be that it's a stupid model and you can do better. This is a fundamental issue. Confidentiality and integrity are opposing goals. You can't have both of them perfect at the same time. Life is just more complicated than that, even in a computer system. So the Clark-Wilson is the compromise, and this is sort of like a modern Microsoft domain. You have just a matrix of things. Subjects are the people, the processes that access things like files and computers and disks, and they have limitations. So you have, instead of this simple 100% integrity or 100% confidentiality, you have well-formed transactions and separation of duties. So you have a certain state where things are in an acceptable security condition, and you introduce new data that comes in which is unconstrained. This is data that you don't necessarily trust. You have constrained data that requires integrity, and you have a transaction procedure that moves data from one state to another, and you arrange that the transaction procedures will maintain security. So once things move into the machine, they will then obey the rules flowing around through the machine and not let anybody break the rules. Separation of duties means that you have, for example, one department collects money and another department issues payments. The same person can't do both, so they can't steal money that's coming in. And this is the general plan of separation of duties: is you have actors that do important things, and you have a second actor that reviews them, so that no one person can get away with something terrible. All right, so those are the basic models. So what model gives you confidentiality but not integrity? Okay, that's Bell. Like I said, they're in alphabetical order: Bell, Biba, and Clark. And the first thing was confidentiality. All right. What model uses alpha, beta, gamma? Okay, that's lattice model. Good. All right, which one has no read up? Okay, that is Bell. Again, that's the simple property. That's how you maintain confidentiality. Nobody can read anything at a higher level. All right. And which one has no read down? All right, that's Biba. All right. So I'm going to record these winners. I've got password. Is that you, Mark?
Yeah.
Good, okay. All right. So then you could consider the information flow instead of just considering one step like read up or write down. This is what Bell, Padula, and Biba use, is they control how the information flows. Read up and write down. Another consideration is the Chinese wall. This is what they do in law companies. If you have two cases that are related in the same law company or the same financial company, you have internal secrecy, like need to know, so that these people don't know what those people are doing, to avoid conflicts of interest. Non-interference is a desirable property of a security system that is very difficult to achieve, but you need this, or you need to do as well as you can at it. This means that the different security levels do not affect each other. Now, if they're all running on the same hardware as virtual machines, then they are going to affect each other. Like if one of them's consuming a lot of CPU, there'll be less CPU for the others and such. But this is the plan. You would like to think that the secret stuff is not in any way affected by the top secret stuff. That's a desirable property. So take grant is another system where you have these rules. You can take permissions, you can grant permissions, create and remove data, and now you can have a complex model of relationships. So Alice can create and remove privileges to secrets. Alice can give Carol access to the secrets, but then Bob can take Alice's privileges away. So you can have as complicated a structure of rules as needed in your system. This is one way to try to simulate the real complexity of modern business and military systems. An access control matrix is what Windows uses and Linux. You just have like read-write access, read-write and execute to certain areas. This person has read and execute but not write. This person has no permission to get in there. That's the sort of thing you'll see with an access control list. There's a Zachman framework that tries to specify the what, how, where, who, when, and why of all these business processes, and then who's allowed to do what, the planner, the owner, the designer, and so on. These are, as you can see, getting pretty complicated, but they're trying somehow to consider all the relative relationships that would happen in a business. And the point is, when you have a small business, you just let everybody have full control of everything. Then when you grow, you start assigning it to people. And then when you get bigger, you have to assign them to roles, because the people come and go and they get promoted and demoted and fired, and you have to just have a role. And people have to fit in their role and get what they need to get in that role. The Graham-Denning model uses subjects, objects, and rules. Things like this: create subject, create object, delete access, transfer access, and so on. And then people have various abilities to do these things. All of these are just different ways of mathematically formalizing the restrictions necessary to run a business. Here's the HRU model. Again, the same thing, but they treat subjects and objects the same, and they have 6 fundamental activities, like enter right into a matrix, delete the right from a matrix, create or destroy a subject or an object, and these rules add up to the constraints necessary to run your business. There are 4 modes of operation for a computer security system: dedicated, system high, compartmented, and multi-level. In a dedicated system is the simplest, and this is the old-fashioned military model where you have an air gap, and this led to people, some told me that there were people in the Pentagon that had 7 computers on their desk for this reason, because you'd have a top secret computer and you'd have to have a whole different secret computer, a whole different classified computer, and a whole different unclassified computer, and they were not connected to each other at all, so that there was an air gap. That's this system. You have a dedicated computer system to handle stuff at one level, and nobody's allowed to use that machine except people who are cleared for that level. This would seem like the simplest way to keep the secrets, and the most expensive and complicated in terms of hardware, but that's easy to understand. Another way to do it is to mix the data on one system, but then make sure that everybody that can touch that system is cleared up to the highest level of that system. Now, both of these first 2 models pretty clearly come from someone who does not trust their computer system. They don't trust the operating system and login and permissions to protect them, so they just want to say the physical access to the device is what's protecting the security here. And that does seem like a pretty good idea these days, as we know all these malware and hacks and everything else. That would seem like the safest procedure, although the most confusing and complicated to maintain. Then you got compartmented data. This is where you have this sensitive compartmented information, where not only does it require clearance, it also requires need to know. So there is a complicated structure of who's allowed to get at things. And so objects are placed in compartments, and you have technical controls that know who you are, and they know what you need to know. Yeah.
So would this be like, let's say you have top secret clearance, but there's something that's considered secret, but you might still not be able to see it because it may not pertain to what you're working on?
Yes, absolutely. So you have top secret clearance, but you work in Moscow. Therefore, you are not allowed to see what's happening in Arabia, even at a lower level, because you don't have a need to know. That's exactly it. That's why you call it the horizontal control. And then there's multi-level. This, of course, is if you really trust your operating system and your virtual machines and everything, you just mix everything on the same machine. People have different sensitivity levels data, different subjects have different clearances, and now you have a reference monitor which is running on the system, which makes sure that everybody only gets what they should get. This is the process that makes sure that the top secret people can access the top secret stuff, but if the secret people try to see the top secret stuff, they aren't allowed to. That's what you trust the computer to sort it all out. This, of course, should be the easiest to deploy and maintain, but the most likely to fail if you're worried about software attacks. All right, so then you can evaluate how well you have done these things. There are various techniques. The original one was the TC-SEC. This is the one people refer to the most, the Orange Book, part of a Rainbow series from the 1980s, developed by the Department of Defense when computers were just coming to being popular. That was the US military model. The European model was IT-SEC, and then they developed common criteria to combine the best of both of them. But a lot of people still go by the TC-SEC rules. This is why, I'm sort of currently, I'm teaching a lot of classes at other colleges and doing a lot of partnerships with other colleges in the world of security, and it's becoming kind of a problem for them that we are not an NSA-approved center of excellence. In order to become one, we have to go through a very burdensome multi-year procedure to meet the 1994 standards for teaching, which have never been updated. And I'm resisting that, but they're saying now some people here are actually volunteering to do it and say we'll get money from it. And I said, well, okay, but anyway, this is the way things are. Once the military has defined something, you keep it like a biblical precept for decades, even as the world has changed and it's probably not that relevant anymore, but still those are the standards. So that is the glorious Orange Book, part of the National Institute of Standards with the NSA, which I think at this time was not admitting it existed. But anyway, this rates security from A to D. So D is minimal protection, like Windows 95. You don't even have to log in. There's no permissions on the files. If you can touch the box, you can do anything with all the files. Then you got discretionary access control, which is like a home PC. You have an owner, and the owner can log in and do anything they want. Then you have mandatory protection, which is like a Windows domain, where there is a boss, and you have to get permission from the boss to do stuff, and the boss gives you a role like system administrator, domain administrator, or just user. And then you got verified protection, which means not only do you have all these controls, but you have layers of management and papers being filed to prove that you implemented the controls, you measured how well they worked, you improved them, and you proved all this with a pile of documents so it can be audited by an agency to make sure that you're really doing all that stuff. And those are the 4 basic levels, and there are sub-levels within them. Then there's the Red Book, which is the network equivalent of the same thing, trying to rate your network the way you rate the other computer systems. And the European system, ITsec, rates functionality and assurance as different. Functionality is, of course, like availability. That's just how well it works. And assurance is the security part of it, aside from just availability, rated in terms of effectiveness and correctness. And you have assurance correctness from inadequate up to the formal model. And these things do more or less map to the American system. The low level is D, then you have the C, B, and then A levels up here. The high E and F levels go up to A1. And they have a few other things here like special high integrity, high availability, and so on. A few more complicated details in the European model, but it approximately does the same thing as the American model. And there's common criteria was intended to replace both of these, so you have a target of evaluation and a security target, defining what your goals are for all your security, and a protection profile for things, specific categories like firewalls, and then an evaluation assurance level of these things, so your system earns a certain score. And you end up with these things. Functionally tested just means it works. Structurally tested, methodically tested and checked, down to the same thing at the high level. Formally verified, designed and tested so you can prove that everything has been done right, and there have been papers filed to prove that it's been managed and controlled. That's the peak, is ISO 27000 essentially, where you have to have a whole bureaucratic structure proving that you're continuously improving. Yeah.
So are we still having the US and the European models, or are we kind of moving towards international common criteria now?
I don't know what's most popular. I know people refer to those Orange Book levels a lot. They are not extinct like you might think they should be. So I don't know the answer. I think it's probably just madness. Probably different people just use different levels. Yeah.
Sam, I mean, if you could give a sign off the top of your head, like a valid, like a percentage value, how much of this like policy is just absolute dinosaur garbage now, like not relevant anymore? I mean, I realize that the government.
I can't tell you about the military. I can tell you about the colleges. They're having to do the same thing. And what happens is we're having to do the equivalent of this level 7 stuff. They call it student learning outcomes. And what happens is colleges, before it comes in, they're doing whatever they do. Then the accreditation board forces you to do it. And for typically, it's a total waste of time. Everybody's just filling out forms they don't understand, filing them. No one knows what they're doing at all. And that typically persists for 30 years before you have an entire generation of teachers pass out. And then it actually turns into something valuable. And I know my sister went through it all at Alverno. And we're in like the first or second year here. So here it's complete garbage right now. But it eventually may turn out to have some benefits. That's what they always say about security and policy, administration, management. You add all these layers of bureaucracy, and at first it just means that they screw everything up. But if they actually get it working, then you have a better product and more. So, and there's always a mixture of the two.
And you get buy-in from the employees too. When the new employees that get onboarded, like they know this is all they know.
That's
and
right.
So they just implement right away. Whereas the old employees, you have to kind of fight unless you can prove to them like, hey, this is actually going to help. And like if you like, and now I worked in healthcare, it was like HIPAA, and it was just kind of like everybody who had like got that beat into their brain, like you should always be thinking about this because the consequences were so severe because they could go after the actual employee. It's not just the organization.
I didn't know that. But yeah, I know at Alverno, they implemented it by forcing the older teachers to just retire. They said, you must do all this extra stuff, and they refused, and they just fired them. So that's typically what you have to do at the end, because it certainly is a whole lot more work for no apparent purpose at first.
Is this for testing systems within like a campus, or is this for testing like Windows as a product?
Well, it is not required for accreditation at a college that you have to be participating in a structure like this.
Yeah.
So you have to implement it to the satisfaction of your accreditation committee. And it moved across the country unevenly. It started on the East Coast, and it took 30 years to reach the West Coast. But it's just like any other industry, like banking or anybody, you have to be up to whatever is considered the current standard. And the current standard, 5 years ago, we didn't have to do it at all. Now we have to do some of it. In 10 or 15 years, we'll probably have to prove we're really doing it all.
So Sam, I guess the biggest way for the college to probably, if they really wanted to railroad this policy through, would be attach all of this to FERPA compliance, because I know in Ed, the FERPA is kind of like one of the big privacy things, and
It is.
FERPA has been written. FERPA was like 40 years ago, and I bet a lot of this electronic stuff predates the law, and so because it's not in there, the schools are not really. Their hand hasn't been forced to comply because they can't like withhold like state or federal grant funding, or they'll tie it to something usually to force compliance. But in this case, like unless there's like a breach and it looks really bad, they usually don't take action until something happens. Or
Well, right, as you can see in the government, there are waves of it. There are governments that are more bureaucratic and try to impose restrictions. Then there are governments that turn off the restrictions and remove the requirements. It's kind of uneven and crazy. That's why it's not as simple as good or bad or effective or not. There's these waves of policy flying around, and your individual teams and managers may be smart enough to make something good happen as a result of the policy, or they might just let themselves be dragged into nonsense by the policy. It's, you have to adapt to the circumstances. All right, these are very good questions. And I think that's really like the job of the CISSP guy is to be smart enough to cope with all this and implement it in a way that actually results in getting work done. Certainly you can implement it poorly and just irritate everybody and fail. But there are opportunities in all this stuff to make a better product if you're smart enough to find the right path through this maze. And what happens, presumably, is if you prove that you've achieved these higher levels, then you get eligible for money and contracts with companies that require that. And that's what people are saying. They're saying if we actually get NSA approval for our security program here, we will get military money. And I would like to have that if we could somehow get it without an intolerable burden of administrative nonsense. So we'll see. There's now motion of it happening. I just said I'm not going to give up teaching to fill out forms for my whole life to do it, which is what it would have taken a few years ago. I'd have to destroy the program instead in order to get this approval. But now we're getting more teachers, so we may have some.
You'll have money for a non-existent program then, Sam.
That is in fact what happens. There are several colleges where that did in fact happen. They have a highly rated program that does not exist. And that's of course the bad part of bureaucracy. You get these absurd situations, like the $900 hammer, where you technically have obeyed the rules, but the results make no sense. All right, looks like we can go. All right, what security feature prevents a covert channel? All right, that's non-interference. If the high-level stuff does not affect the low-level stuff, then there is not something to measure at a low level that leaks secrets. The classic example is if you watch pizza deliveries near the Pentagon, you can tell when they're making major military deployments because everybody has to stay late and order pizza. All right, so which operation mode enforces an air gap between each security level? Okay, that's dedicated system for each thing, not compartmented. You have a separate dedicated system for each level of security. Not a popular answer, but it's correct. So which operation mode uses a reference monitor? That's multi-level. Yeah. By the way, once you learn these terms, you will see them in Microsoft technical documents for technical support. All the operating systems have components with these names to meet these requirements because they all want to sell to the military. And so they have these components built in, like the trusted computer module and such. Anyway. All right, what TC-SEC level is your home Windows 10 laptop on? It's a C, because it's a little bit better than Windows 95, it was a D. You do at least have to log in and prove you're the owner, and then you can do anything. So that's a C. All right. What's the modern international evaluation method? Okay, that's common criteria. That's what's common about it, both the US and Europe. All right, so Anna times 2, Sidewinder, password times 2. Okay, good. Get your name later. Anyway, good. So let's see if we can do one more of these before a break. All right, so secure design concepts. So you have layers. This is a fundamental way computers work. You have the hardware, and then above that you have the kernel, which directly touches the hardware, and above that you have the operating system, and then the applications above that. And the idea is you can have stuff at one layer that doesn't affect another layer, so you can divide the work. Abstraction is a fundamental property where you do not present users with all the information. You let them see just information at the right level. So when you're writing an email, you just see the text. You don't see IP addresses or circuits or voltages or anything. All that is happening, but you don't need to know that. You look at things at a more abstract level. Now you got security domains. So the kernel mode is the low-level access directly to the hardware. User mode is above kernel mode, where you don't directly touch the hardware, you run programs, and therefore if you make mistakes in those programs, they don't crash the whole machine, and so on, because errors in user mode should not affect kernel mode. Hardware has 4 rings of security, but only 2 are actually used by any modern operating system, Linux or Windows. They just use ring 0 and ring 3, except for hardware virtualization that breaks the mold, which is the way it always is. Every rule in computing is only true up to a certain point in history, and then they make it more complicated. So hypervisor mode is ring -1. And this is why a lot of students install VMware and then they can't get it to work until they reboot their machine and go into BIOS and turn on hardware-assisted virtualization. This is Intel VT or AMD V. This is the virtualization assistant, which lets your virtual machines run in ring 0, and it controls their access, so they call it ring -1, above ring 0. So it made it a little more complicated in that regard, and that is optional new chips on the board that are turned on by turning on those modes. Or new probably firmware on the board. I don't know exactly where it's implemented in hardware. But all the computers have had it for the last 10 years, but they almost all have it turned off by default, but you have to turn it on to run VMware. All right, you can have an open system where the chips are numbered and you can buy the chips and anybody can build it and the standards and everything are available, like IBM PC. Or you can have a closed system like the old Macs before they switched to Intel, where everything is secret. You can't buy those chips, you can't build your own, you just have to buy it from them. All right, so the system unit is the main tower unit that has the hardware in it for the essential things like the CPU and the RAM and such on the motherboard. The bus is the line that moves data from one component to another, like from the CPU to the hard disk, or the CPU to the keyboard, or the display. There are, in fact, various different bus lines at different speeds. In modern computers, there's the North Bridge, which has the high-speed data moving from the RAM to the CPU to the video memory, and then you have the South Bridge, which is slower, going to the slow things, like the keyboard and the hard disk. You hear this North Bridge term for modern computers. The CPU does all the processing, all the logic and arithmetic units are done by the ALU processes, and it has a control unit which fetches instructions and keeps track of which one you're processing. So there's a cycle. You fetch an instruction, you decode the instruction, then you execute the instruction, and then you write the result somewhere. And that takes 1 clock cycle. And most instructions take 4 or 6 clock cycles to do things. Interrupts are signals that demand immediate attention. They do not wait for their turn. They raise an exception and say, wait, you have to deal with this problem right away. Like shutting off your computer is a request to shut down, stop what you're doing, and so on. There are lots of interrupts flying around modern machines. Early machines like MS-DOS could only do one thing at a time, so if you're printing, you have to go get a cup of coffee because you can't do anything else until the printing stops. Modern machines are multi-processing, so they can run, they're multiple threads. So there were multiple processes at the same time, and each process is broken into individual threads of computation, so that if one of them is waiting for something slow, the other ones can move forward. Multitasking is all modern systems where it can run several programs at the same time, but it's not really doing more than one program at a time. It's strobing between. It does one program for a while, then it suspends that operation. It does another program for a while. The appearance is they're all moving forward, but in fact, they're each just getting the turn of the one processor, unless you have more than one CPU. That's multiprocessing. And then you can have symmetric or asymmetric multiprocessing, where you have one operating system with many CPUs or a separate operating system for each CPU. And those computers can be doing multiple things at the same time because they have multiple CPUs. The watchdog timer is one of the things that notices that the machine has crashed and then reboots the system. All modern computers are CISSP, complex instruction set. There are something like 10,000 assembly language instructions on the Intel processors. There used to be Motorola processors that were reduced instruction set computers intending to have a smaller set and make it faster, but that did not win in the marketplace, but now it has come back for cell phones. ARMs are RISC processors. So direct addressing is when there's immediate values. You can just add the literal number 8 to EAX, and then the number in the EAX register will go up by 8. Or you can add the contents of memory address 8 into EAX. That's called a direct address. You have a number that points over here, and then there's an indirect address where you go to the contents of something like EAX, and then you take that and find the address there and add it in. Those are the modes. You can refer to a direct number immediately, you can have an address immediately, or you can have a location that contains a number, and that number is an address. They call that pointers in C. Those are the common modes. One process cannot affect another process because they have memory protection. You're going to need this for multi-user and multi-processing systems so the different processes don't conflict with each other. They call this process isolation. There are various techniques. Virtual memory and object encapsulation. All Microsoft Windows programs think they're running at the same address. They're all running in virtual memory space, sort of like a virtual machine, only much simpler and much less separated from another machine than a virtual machine are. Yeah.
Wasn't like Windows 2000, Windows XP the first one to do protected memory? Like that's why the system didn't crash as much. Like the one crash process wouldn't take the whole system down.
There was a big step forward. I'm not sure exactly how much of it was new, but yes, Windows 2000 was Microsoft's big step forward. When 95 and 98 would just crash and die all the time, and so would NT. And with 2000 was the first Microsoft server that could actually stay up for more than like a week or two without crashing. And they were sued at the time saying they actually stole that code from Linux. But that lawsuit mysteriously shut up and vanished. I think they paid them off. But anyway, it was much better.
Because one program crash a lot of times, like it was a 50-50, like you'd go to Task Manager and it's like, okay, if we don't kill the process in Task Manager, like the whole system will blue screen and you lose everything.
Absolutely. Yeah. Anyway, so real mode, when computers start, they go through their historical history. They start in real mode where they only have a very small amount of memory and no process isolation. This is the days of MS-DOS. And then they switch to protected mode later and actually have the rest of the memory. Although the 64-bit processors have a different process than this. So virtual memory is what I was mentioning. The processes all think they're running at a fixed location, like 400,000 or so. That isolates them so a process cannot refer to memory in another process. Can't read or write over there, that's how it works. You can swap in pages in and out of RAM, and the kernel, of course, can access everything. If the kernel tries to access memory in swap space, you get a page fault. That's because the kernel reaches for memory, but it's not there. This is how your machine can run virtual memory, where if you open a browser and you open Photoshop and you open another thing, after a while you've used up all your memory. If you try to open the next thing, it could give you an out-of-memory error, but it doesn't. It takes some of the stuff that should be in RAM and puts it on the hard disk and opens it. And now some of the programs are running, but what they need in memory is not in memory. And when you return to that program, it has to swap data back to get the data back in RAM, so it runs more slowly, but it runs as if it had more memory than it has physical memory. That's virtual memory.
That's trashing, right? When you're going between.
They call it thrashing. Yeah, if you don't have enough RAM and you're constantly going to the hard drive, they call it thrashing. So your drive everything runs really slowly, and your hard drive is scrubbing away, trying to replace all that memory. So BIOS is the code in firmware. When you first start the machine, it runs this code, which almost never changes. It does a power on self-test to detect all the hardware, because for all it knows, while you had it turned off, you installed something like a different monitor or more RAM or something. So it does post to see what it's got, make sure that it has a keyboard and some kind of boot device like a floppy or a hard drive or something. And if it finds one, it tries to boot from that. You can have write once, read many devices like CD-ROMs. This is one place to put data so you won't have it changing on you. The Trusted Platform module I mentioned is a cryptographic coprocessor having the name referred to in the military designations, so that it creates the trusted platform to make accepted military level computing. And this is the hardware processor. This is a place to put cryptographic keys that cannot be stolen by any kind of malware, because they are not anywhere in the address space of the processor. The processor cannot read the key. All it can do is ask the TPM, please decrypt the disk so I can boot up. And the TPM has the key, and your processor can't get it. That's the idea. It's a trusted place to handle cryptographic processes, and that's what happens if you have full disk encryption like BitLock. Data execution prevention is a big step forward that came with Vista and Windows that prevent buffer overflows, and a lot of other attacks were playing games with it in the exploit development class. Now RAM has permissions. Areas of RAM can be marked non-executable, so you can store data in them, but if somebody tries to store code in there and run it, it won't run because it's not executable. This stopped an entire generation of buffer overflow attacks. There are ways around it, but it raised the bar. ASLR is another one. This way, instead of every program just launching in the first available spot of memory, it randomly chooses a different spot in memory every time you reboot the machine, so you don't know where you are. Every program thinks it's at 400,000, but where it really is, you don't know. And that means it's much more difficult for attacks to work because if they inject code, it's hard to find where your code went. There are ways around this also, like heap spraying, but again, it raises the bar. And I got a few hoots about that stuff. Okay, what CPU ring is user mode? Okay, that's ring 3. All right. Users can't handle the truth, so the computer lies to them. What is the term for that? That's abstraction. All right. What's the communication channel between components? That's the bus. All right. If I launch Microsoft Word, what has been created? It's a process, which is a container containing several threads. All right. And where's the cryptographic coprocessor? All right, that's the trusted platform module. So I got password times 3, E, and me, MEU. Now, I was thinking of having a break, but I think we need to cover one more section. Let me do that, and then we'll have a break while the people set up, because several students came here with presentations to give. So during the break, you'll have time to set them up so we can use the other computer. So I normally wouldn't go this far without a break, but in this today, we'll do one more section. People don't seem to sleep yet. So, secure operating system. Right, so the kernel is the heart of the operating system, running at ring 0 that has direct access to the hardware. There are 2 types. The monolithic kernel is what old things like Slackware Linux had, where the kernel runs in supervisor mode, and if you want to change anything, you have to recompile the kernel every time you add another hardware driver or something. This is, of course, simpler, probably runs faster, perhaps more secure, but less versatile. Most people prefer the microkernel model, where you can add loadable kernel modules without having to recompile the kernel. That's much easier to use. The reference monitor we mentioned, this is the part of the operating system that watches all the access, every subject trying to reach an object, and decides whether it's allowed to happen according to the security policy. So you can supposedly have multiple levels of security on your machine at the same time, and it will sort out the users and the objects and make sure that only the right people see things. This is what you must have for levels A and B of TCSEC, unless you use an air gap separating the systems. Linux and Unix use read, write, and execute for user, group, and others. So you have these 9 letters: read, write, execute, read, write, execute, read, write, execute for the owner of the object, people in the same group, and everybody else. That's the Unix permission system. Windows uses this stuff: read, write, read and execute, modify, and full control, and you have groups like everyone and administrators and users and so on. It's a different model to accomplish the same thing. SetUID programs in Linux are ones that run with the permission of the owner of the program instead of the person running it, because a normal user does not have the ability to write into, say, the password files, but in order to change your password, you must. So the password command, PASSWD, is an SUID program. These things are risky. The more of them you have, the more chance of an error leading to privilege escalation. If you get your OSCP certification, you learn to scan and search for these, because an extra SUID program is often a doorway to escalate your privileges. Virtualization is, of course, all the rage. Everything you connect to in the way of a server these days is actually a virtual machine, so it's running on a hypervisor. The hypervisor is software that simulates hardware, so when your computer thinks it's putting something in RAM, it's simulated RAM, and thinks it's putting on a hard disk, it's a simulated hard disk. Full virtualization is what you get from things like VMware Workstation. It simulates the hardware, and you run an entire OS inside there. This is the most secure, but it's also the most expensive. most overhead. Para-virtualization runs faster, where the simulated hardware actually matches the real hardware. So they all see the real network card, they all share the same driver. This is faster and more efficient, but it's not possible with closed OSs like Windows. So the hypervisor controls the interface between the guest OS and the real hardware. Type 1 hypervisor runs on bare metal like ESXi. Type 2 runs on top of an operating system like VMware Workstation. So you're running Windows and then you're running Linux on top of Windows, which is of course slower and more wasteful, but more versatile. So this makes your hardware cheaper because you can get full value out of the hardware. Before virtualization, most servers were running only 20% of load. Now you can put enough virtual machines on there to run them more like 80% load. Therefore, you have less power and cooling. It's easier to make snapshots, easier to make clusters by duplicating machines, and so on. It turns out to be enormously valuable. So everybody's running virtual machines for practically everything these days, except end user devices, which are mostly not, because they only want one OS and they want it to run fast. This leads to a lot of security issues. If you have multiple guests on the same host, then obviously they can all go down at once if there's a hardware failure. And there are also cases in which vulnerability in one guest lets it escape to the host or to other machines. And this was one of the things that got people very upset about Spectre and Meltdown. Spectre and Meltdown allowed VM escape, so one VM could go affect the other VMs. And all the major cloud providers had to rush and patch it right away. And as we all saw, there were lots of problems because the patches really don't work very well. Another big issue is if you run virtual machines, you now have virtual network traffic that doesn't always go through real network adapters. So traffic from one VM to another doesn't ever get picked up by your intrusion detection system or your monitoring because it never passes through any real NIC. So you're going to have to add some kind of virtual monitoring for it. And as we move into software-defined networks where all the networks are virtual too, we're going to have to move all the security appliances into that virtual world to keep up with it. And right now we're in the in-between stage where a lot of traffic is not being picked up. Another related issue is multi-path TCP. A lot of people have more than one internet connection and they use them both, and when you have one download, some packets come through this one and some packets come through that one. So if you're sniffing at either one place, you don't really get the whole stream. Yeah.
So does that mean that with virtual NICs and stuff, like there's potential that you could infiltrate and maybe not get picked up and you slide by the IDS?
Yes.
Yes. And then once you're in, you have a pivot point to just exploit the entire VM stack, which could be like 50 or 100 critical servers.
Yes.
And they'll never know.
Yes, that's exactly it. Especially with things like Spectre and Meltdown. I could infect one VM, attack the other VMs, and your IDS never knows it's happening.
And a lot of times people only have one ESXi hypervisor that has all of them running, so you basically get the whole run of the whole
Yeah, maybe
stack.
6 years ago, I rented a virtual machine server, and I tested, and there were 178 other servers on the same layer 2. I could have attacked any of them.
Are there controls to limit sensitive information in the VMs?
The cloud providers don't provide any. This is the most common misconception. Most people think their cloud provider is providing security, and all the cloud providers are very clear that they do not provide security. That is your responsibility. They just give you availability, and they don't even tell you how many people you're sharing the same hardware with, or unless you pay extra. That's why Microsoft makes it clear they won't even tell you what country you're in unless you pay extra. And you don't even know how many extra copies they're making or backups or anything. So it is a big issue, and it's tough. And if you want something like HIPAA compliance, Amazon will provide it for a price, and then you have to read very carefully what they're really providing.
So you have multi-tenancy issues where you could attack multiple companies if they're all happen to be on the same hypervisor?
Absolutely.
Oh no, I was going to say you can buy dedicated hardware.
Yes, you can. And that's why some people prefer private clouds, where you do buy your own servers, and then you control this stuff. If you use a public cloud,
Or-
you've lost control of all that.
At Amazon, you can have your stuff put on dedicated if you pay more.
Right, right. Or you just lease real hardware. That's why, first everybody rushed to the cloud, then they realized maybe they shouldn't just be putting everything in the cloud, especially now that everybody and their brother is leaking stuff in Amazon containers these days. Yeah.
Is it possible? I've heard that there was a way, I think it was University of Maryland came up with a way where you could selectively route your packets so that they did not go through specific countries? Because if you
Yes.
certain countries, like you said, when UCSF subcontracted like 3 times over, and it was to go to like Pakistan, and there's no HIPAA controls, like they could prevent their data from egressing certain routers.
Absolutely. And that is a service that people are willing to pay for to make sure that your data stays in the country and that you know how many backups there are and so on. All right, so the cloud computing is out there. You can get infrastructure as a service or platform or software as a service. This is where you just use a program somebody else wrote. This is where you have a server you control completely, and then there's in the middle where you have a general purpose server like web hosting. These are just different things you can lease from a cloud provider, and it has different balance of how much they provide and how much you provide. So private cloud is what you use if you buy your own hardware and then just make it available on the internet to some people like your trusted employees. This is, of course, the safest if your employees are competent enough to keep it secure and available. The public cloud is the simplest, where you use something like Google or Amazon Cloud, but then you really don't know where your data is or how many copies there are or anything unless you negotiate a service level agreement with them, and then you have some degree of confidence that they're actually only doing the approved things with your data. Yeah.
I heard at the Cisco class that they've got a new term on private cloud. They call it fog now.
Oh, they call it fog?
Low to the ground.
Oh, that's good. Okay.
Cloud low to the ground.
Yeah, that's not bad.
Buzzword.
Okay. Buzzwords are super important.
Yeah.
All right, then there's many things have gone wrong. Amazon had public images that were distributed with a backdoor SSH key, which is very easy to do. Amazon also, when they first had their virtual machines, they forgot to wipe the disk between one customer and the next. So all you had to do is install a forensic tool and you'd see the last guy's data on there. It's an issue, of course. That's why Kyle Rankin, who will be giving a talk here later this semester, is one of the Linux experts. He writes a lot for Ubuntu books and Ubuntu magazine. He figured out a way to wipe your cloud device and make sure it's wiped before you let go of it, which is a pretty good idea, and most people do not know how to do that, so they are at the mercy of their cloud provider who promises they do that, but they don't really know it happens. Grid computing is another way, where you use other people's machines to contribute to your project, like SETI at home, or Bitcoin mining, where all these random people, God knows who they are contributing to the task. And of course, that means you have concerns about the integrity of it all. The parallel systems can give you high performance if many CPUs are all working together, sharing memory, but then you can have race conditions where one of them changes the memory location and another one changes it in another way, and that creates brief moments of vulnerability. This is very common in systems that write to the temp folder on Linux, and that's called race conditions, and you can exploit the system by winning the race. One famous example was the dirty cow exploit on Linux. You could escalate privileges by winning the race. Applied to everything. It was patched a couple of years ago. Peer-to-peer like BitTorrent is another way to get many computers to work together, so you can download a file from many machines. The problem is you're now getting that file from many sources and you really don't know if it's been altered, so most BitTorrent clients have a hash value. They're supposed to have a hash value of every shard to make sure it's accurate. Thin clients is another way to go, where you don't even have a full computer. You have a very minimal computer like an iPad or just a browser, and all the computing is done somewhere else. It can be hardware or software based. This is what a lot of people do for security, so that you don't even have a copy of the data. You're just viewing the data on a server, and now I can control the security at the server. Diskless workstations are similar. There is no local storage. You load everything from the OS into RAM over the network and run it there. And when you turn it off, it forgets everything. And of course, the Internet of Things is the commercialization of all this, where you buy refrigerators and you have webcams and everything, and it's all running tiny little OSs that are usually very poorly designed, because the number one issue is to make them cheap. And they typically have an endless array of awful things like default passwords and old versions and built-in backdoors, and that's why we have a lot of issues right now, as everything is connected to the internet without any clear security standards. We'll do the cahoots here. Okay, what do you need for TC-Sec Level A? Okay, you need a reference monitor. All right. What's the security risk of virtual machines? Okay, VM escape. All right, Canvas, where you take your quizzes. What kind of service is that? Software as a service. You can only use the options the programmer gives you, nothing else. All right, if you combine dissimilar computers together to get more CPU power, what are you doing? Okay, that's grid computing, like SETI at home. All right. Put that thing on, you know. That's good. Lovely. Good. And once you get your slides going and the microphone set up, I'll start timing you. I will warn you when you're down to 1 minute. Okay, you set?
All right.
Go ahead.
All right. Good evening, everybody. My name is Eric. My presentation this evening is going to be on the big picture, transitioning from a technician to a manager, which is kind of the whole idea behind the CISSP. A little bit about myself. A little over 12 years of IT experience as an IT in the United States Coast Guard. I began my career in the help desk, where I learned valuable customer service and basic troubleshooting skills that I still use today. As an IT, I've worked on various hardware and software platforms throughout my career, different places I've been stationed. Mostly it's been very technical for me until recently. My last station I was at, I was an information system security officer, so I dealt with a lot of the security stuff that we're touching on in this class, and I'm kind of beginning that transition from tech to manager, so to speak. So here I'm at CCSF to marry academics with my experience. Just trying to kind of get those two brought up together. So just a real quick touch on what the CISSP is, which we've already kind of talked about in this class. What makes the CISSP more managerial than technical, and what is the big picture. So this is straight from ISC squared. The CISSP is the most globally recognized certification in the information security market. Validates an information security professional's deep technical and managerial knowledge and experience to effectively design, engineer, and manage the overall security posture. So this is kind of where, yeah, it's important to know that all that techie stuff that we've all kind of learned along the way really dives into how do you at the top implement all that stuff. How do you design it? How do you engineer all that stuff? And going through these 8 domains here, which we are halfway through here, we're going to hopefully learn a lot of that and kind of transition from that technician role to that managerial role. So yeah, it's definitely a lot of information for sure. So most of us have spent a good amount of time as technicians in some capacity, whether you've done that in a job or just at home or just kind of nerding out or whatever. It's a totally different mindset as I'm learning myself from that of an IT manager. A technician or system administrator, if you will, is very narrowly focused on whatever their world is at the time. That is quite the opposite of a manager. On the other hand, they need to stay out of the weeds. To pull themselves back up, they need to see the larger picture of everything, which is kind of what CISSP is doing here. We're focusing more on like a macro level, whole view. But I just want to reiterate and be clear that both are needed in an effective organization. They're very important, both roles. One's not more important than the other. So I kind of did this little graphic here. To me, this is kind of the big picture, right? We spend, for me, and maybe for some of you, you might have shared this experience. I spent a lot of time as a tech. You know, you have all these different technicians down here, and you're kind of just focusing on one of these, 1 or 2 or maybe 3 or 4, depending on what your job or your role is. And you don't really see more than that. So you might have this narrow focus of here, 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 and that's going to be the same, you know, depending on what your role is or what your job is. But an IT manager, on the other hand, their role is to see all of that. Their role is to see the big picture. So that's kind of my whole, you know, that's kind of the whole thing on the CISSP in this class is I kind of want to transition from just, you know, this narrow focus down here into seeing that whole big picture and getting all the domains. So with that, thank you. I would like to answer any questions you might have.
Okay, great. Thank you. Good. Thank you. fitting the time. So, good. You want to go ahead? Okay. Good. Okay.
So this is a perfect contrast to the last one. Literally, Wireshark would be the microscope, and the manager would be the big picture. But it's a good to know as a manager when your network security guy is bamboozling you. So my goal for this is to give you an idea of where it can be used, the types of problems that it can be used, and how you have to go about it to get that to work. A good use case for a Wireshark could be something's working on this computer, it works fine, and you go to a different building, a different location, somewhere else on the network, and that computer is not working the same way. And you've tried absolutely everything that you know how to try, and it still doesn't work. You've got the same software, you've got the same configuration. There's something in the middle that's not happening, and it's not working right. So that's a good use case for the microscope, because you've already done everything else. So typically this is done by a very high-level person that has these actual tools at their disposal, and they know how to use them. And the key is you've got to get the Wireshark looking at the same network that device is on. And it can be either side or both sides, like the server that it's trying to talk to and the device, or maybe different segments of the network. And with the cloud, this is the perfect thing. Before the technology that it used to do Wireshark was called a sniffer, and it was actually a luggable device with dedicated hardware, and you really didn't have the software option where you could put it on the local machine. And you can actually install Wireshark, I'm sure, on the cloud. They may even have it on the cloud, so you can actually run it in the cloud, which is cool. Dubious and dangerous, but whatever. You can sniff on the wireless networks too. And the one peculiar thing that I noticed about wireless is unless you're actually connected to the same SSID, at least on the version of Wireshark that I'm running, you don't see anything. It's like it's not even plugged into the network, which is cool. It kind of behaves like a physical connection. And then Ethernet, and it's basically you really have to be sure that you're looking at what you're really looking for. It's got to be on the same broadcast and collision domain, which means it's basically literally almost the same physical port in today's networks, because almost all networks are switched today. There's absolutely no place that you should see a hub, which means that if you have a switch network and it's a cheaper switch network, then you may have to get creative on how you do this, especially if you can't install the software on the workstation. That's when an actual old school hub actually comes into play, where you're like, oh, I can just kind of plug in where the user was plugged in. So on the right is a switch. It's probably a cheaper non-managed switch. And on the left is like a pocket hub. They used to be called repeaters. So what's the difference? And basically a hub, anybody talks, everybody listens. They're all seeing the entire scope of the traffic that's going on in there. And in a switch, not the case. There's individual conversations get established, and you can be plugged into that same switch and you won't hear what's going on between this workstation that you're trying to look at and the server. So, the bottom line is, with a switch, you really want to get a managed switch like a Cisco or something higher end, so that you can actually mirror the port. And like one of the earlier slides that we looked at in Sam's stuff, there's an IDS that's typically plugged into the span port.
1 minute.
So basically that's what you want to do. So you've got workstation A talking to B, and you're actually looking at all that traffic with a separate port on a switch. But if you don't have that option, you can always plug into a hub. So the blue line is the original PC plugged into the switch. You can unplug that blue line, plug in a hub where that's supposed to be, plug the user into the hub and yourself into the hub, and then you're all of a sudden you're seeing all that traffic, which is cool. So basically the flow is you capture some working traffic, so you know what that looks like. You plug in, you capture the non-working traffic, you compare and look for the differences. You may need to repeat it on both ends. So my example is DHCP wasn't working on this network, and one of these switches in the middle, at this layer or this layer, just wasn't broadcasting.
All right, well, that's time.
That's it.
Thank you.
Okay.
And what's your name, John Emery?
John, yes.
Good, okay. Good, thank you.
My name is YK. I'm going to talk about interesting CISSP exam questions. These questions are either I have to interesting or I have to do some digging to find the answer. One of the question is separate violation tracking and analysis. Parameter is the data manipulable level. The four choices are quantity baseline, maximum log size, circular logging. The answer is keeping levels. The keeping level is the established baseline for violation activities. There may be normal user errors. And for violation tracking is whether violation is either occur or just the implementation is not there. The analysis is just to find out the trouble spots, the security and usability. This is one of the questions. Second question, three principal scheme to provide framework for managing access control. Answers discretionary access control and mandatory access control and role-based access control. And the other three options in the data control include non-existing control, like the layer-based access control and target-based access control. Those are not. Next question, which following backup analysis is most expensive. They're cold, hot, warm, and answer is hot. Backup site is the way data centers will be recreated. For cold backup, is just have a building, have a space, and warm backup is have the space and then also have the hardware. And the hot backup is a mirror image of your data centers. And so all you need is waiting for the backups to get it running. With following recovery issues, considering disaster recovery planning. The reason I picked this one is because a little bit odd. The question, the options are continuous salaries and expense disbursement is more worried about, and the answer is public relation. Then the reason is it's just odd that people are worried about not paying the bills, and then it's more worried about public relations. This question is part of chapter 4 in our book. It's next week's class. It's talking about a Class C 5 suppression system compared to the Class A 5 suppression system. The Class A is like combustible material like wood, paper, and Class B is like flammable liquids, and Class C is electric fire. And the answer is electrical fire, electrical equipment. And one interesting thing is in Europe and in Asia, the Class C is chemical flammable. And this question to talk about dry pipe sprinkler systems. For dry pipe is mainly used in cold weather, where like outdoor parking lot. Basically, the pipe is filled with air at low pressure, and it's just like it's for stopping the water leaking. This question is what is used for suppressing combustion through a chemical reaction kills a fire, and all those four options are actually using for killing fire, but the answer is halon. Halon is non-electrical, non-conducting gases for fire extinguishing.
All right, better stop.
Okay.
It's 5 minutes.
Okay.
Thank you.
Okay.
All right. And I think there's another one, right? There you go. Stop. Good.
Hi everyone, my name is Mustafa. So last week I went to a cybersecurity summit in San Jose. So the cybersecurity summit is mainly talking about new solutions to how to find the threats and how to prevent having these threats. Point about this security, it's made for all the executive that work in tech companies in the Bay Area, and they got most of the security experts that work in the Bay Area also. So most of the talks in the summit. Okay. So the first talk. It was this person from the FBI cybersecurity branch in San Francisco, and he was mainly talking about the new threats that we will be facing in 2018. And the rest of the summit was mainly talking about products and solution, how to detect and prevent all these attacks and threats. And one of the interesting things that they were talking about how to implement the AI section into finding these threats, and if the community and public is ready to have something like that. And also one of the most important things that most of companies right now have to implement some procedures to make everyone work for the company to be aware of security. Because human is the weakest link in any company, and that's how we get attacked and we get breached. So some of the threats for 2018, the main problem is ransom. Ransom attacks has become one of the main issues lately, and they make lots of money out of ransom attacks. Whenever you get ransom attack, you have lots of breaches and you lose lots of your data. And we have been seeing that happen to lots of companies, like for example, Equifax, and they lost more than around 200 million record from very important social numbers and all our data. So we need to find something to stop that. And there have been lots of problems now because right now we have lots of devices connected to the internet, not just phones or laptops. You can have all your house connected to the internet and control it from everywhere. So we need to be aware how to keep this secure. So lots of crazy things can happen. And how right now, most of the hackers has became very smart to find new ways to hack and find exploits and vulnerabilities, and to find whatever they need just to hack and get whatever they want. And the last thing they're talking about how to implement the AI and how to make sure how to make it implemented to find the actual threats and to prevent them.
Is there anything you can buy with AI yet?
I think they have some solutions, but they are still in the prototype.
That's what I thought.
But nothing ready yet to be sold.
Okay, thank you. Hey, fit in the time. Did anybody else want to talk today? Are you ready? Yeah, go ahead.
My talk is on virtualization. My name is Nina. So what is virtualization? As we know, today's 86 computer hardware was designed to run a single operating system with a single application, leaving most machines vastly underutilized. And virtualization lets us run multiple virtual machines on a single physical machine, with each virtual machine sharing the resources of that one physical computer across multiple environments. Different virtual machines can run different operating systems and multiple applications on the same physical computer. The usual goal of virtualization is to centralize administrative tasks while improving scalability and workloads. Virtualization is the creation of a virtual rather than actual version of something, such as an operating system, a server, a storage device, or network resources. And we probably have done this on our own when we have divided a hard drive into different partitions, the logical division of a hard disk drive to create, in effect, two separate hard drives. And there are types of virtualization in 6 areas of IT where virtualization is making headway right now. The first one is network virtualization. It is a method of combining the available resources in a network by splitting up the available bandwidth into channels, each of which is independent from the others and can be assigned or reassigned to a particular server or device in real time. There is the storage virtualization, which is the pooling of physical storage from multiple network storage devices into what would be a single storage device that is managed from a central console. And storage virtualization is commonly used in storage area networks. Server virtualization is the masking of server resources, including the number and identity of individual physical servers, processors, and operating systems from server users. The intention is to spare the user from having to understand and manage complicated details of server resources while increasing resource sharing and utilization and maintaining the capacity to expand later. Data virtualization is abstracting the traditional technical details of data and data management, such as location, performance, or format, in favor of broader access and more resiliency tied to business needs. And desktop virtualization, as we know, is the virtualizing of a workstation load rather than a server. This allows the user to access the desktop remotely, typically using a thin client at the desk. Since the virtualization is essentially running in a data center server, access to it can be both more secure and portable. The operating system license does still need to be accounted for, as well as the infrastructure. And application virtualization, this is the abstracting the application layer away from the operating system. This way the application can run in an encapsulated form without being dependent upon on the operating system underneath. This can allow a Windows application, for instance, to run on a Linux and vice versa, in addition to adding a level of isolation. There is a video which is about 2.5 minutes. I'll try to show at least the beginning. And it's super simple. No thanks.
Over the years, IT complexity has grown while efficiency has plummeted. Virtualization reverses this trend, simplifying IT infrastructure so you can do more with less. Virtualization lets you run your applications on fewer physical servers. Through virtualization, each app and operating system live in a separate software container called a virtual machine, or VM. VMs are completely isolated, but computing resources, CPUs, storage, and networking are pooled together and delivered dynamically to each VM by software called a hypervisor.
1 minute.
Every application gets what it needs for peak performance. With all your servers running at full capacity, you don't need nearly as many. Hardware count and overhead drop dramatically, while application performance improves by leaps and bounds. Bottom line, greater value at lower cost, with less complexity and faster maintenance. Now you can spend more time on innovations to meet real business needs. But all virtualization is not created equal. For the smallest companies as well as the largest global enterprises, VMware is far and away the most trusted and widely deployed platform. Our technology is the most mature, feature-rich, and reliable, generations ahead of any other.
And that's for VMware, of course. And just to finish up, what I wanted to mention also is that, I guess it's here. Okay, well, where's my last slide?
Well, you've run out of time.
It's right here, that you can take CNIT 151 if you're interested to learn more about virtualization.
Okay, thank you. All right. Anybody else?
Is that the intro to virtualization or
Yeah.
VMware?
Intro, I think. Yeah.
Yeah, it's intro. I'm in the 151 class.
Yeah.
Well, good for them. These folks get extra credit. Next week is the general time to do it. You're going to get normal credit, and after that, people lose points for being late, so you should follow in their footsteps.